So I'm going to start the chapter of electrostatics, one of the chapter from class 12, and the portion I'm going to explain is the electric field. This portion of electrostatics is most of the times asked in JEE and NEET. Questions are very relevant from here, and the questions from this portion are multiple concept based because they're having concepts based on mechanics also. Fine. That is, when we're going to solve the problems from this portion, from the process of electrostatics or the electric field, electric potential, they include the concept of electrostatics as well as the concept of mechanics along with. One portion that I'm going to explain, one topic you say, is the Coulomb's law. Most of the times we're having some misconception in this portion. Later I'm going to explain what misconception we face most of the times. So we will know that when two charges are placed or when two charges are there, separated by some distance, a force of attraction or repulsion acts between them. If the charges are of same polarity or the same nature, a force of repulsion acts between them, and when the charges are of opposite nature, a force of attraction acts between them. We can check here. And this force remains inversely proportional to the square of distance between the charges. That is what the Coulomb's law says. If you are having two charges separated here by some distance r, the charges are q1 and q2, a force of attraction or repulsion acts, that is q1 q2 by r square. This proportionality can be replaced by a constant k. This k is called the electrostatic constant. And the value of k is 1 by 4 pi epsilon. This epsilon is basically the permittivity of space, permittivity of a medium, we say. And this is actually it is also called relative permittivity. Relative permittivity is because it is the permittivity of a free space to a given medium. That is what we say relative permittivity, and we write that epsilon r. Now, what the important property and what the important limitation of the Coulomb's law is? First of all, the limitation I will explain you. First of all, this Coulomb's law is applicable, or the Coulombian force between two charges is applicable for point charges at rest. It is one of the most important factor. It is applicable for point charges at rest. Limitation 1. For point charges at rest. See, why point charges should be there? If we consider an extended body in place of 2 point charge, will the Coulomb law be applicable to them? What I'm saying? In place of 2 point charges, if I consider two big bodies I'm having, and I'm going to apply Coulomb's law over there. Can I do so? Let's see what happens. See, I'm explaining you the only important concepts that, like you say, a quick revision of the chapter is there. That is the checkpoints I'm going to deal. So let me explain this. How the Coulomb's law act for 2-point charges. Suppose you are having two big bodies separated by distance r and charges distributed over these bodies. Due to the effect of induction, due to the effect of electrostatic induction, what will happen? The charges will be shifted this way. I'm considering the same polarity of charges over there. That is, the two bodies are having at same polarity. So, if the charges is going to shift this way due to the effect of induction, the thing will, the distance between the center of mass, the distance between the center of mass of these charges will be also changed. This is the R effective over here, and this R effective value of R is greater than the actual distance between the bodies. If we are going to consider the opposite nature of charges, obviously the relative distance that between the centers will be decreased. So overall, what is happening? In both the cases, the actual distance between the charges is different from the distance that we have got when the charges are induced on the body due to the effect of induction. And this induction effect causes the relative distance, the effective distance between the centers to be changed. So obviously, we can see in the first situation, the effective value of force, that is, here the force is inversely proportional to the distance, square of distance. So the effective value of distance is increased, the force will be decreased. And in this case, since the effective value decreases, the force will be increased. So we need to be very careful when we are going to apply the Coulomb's law. So basically that is why it is applicable for point charges, because in the condition of point charges there is no effect of induction between the charges. Fine? Okay. Now also in situations in which the problems are basically asked in the portion of G. See. Suppose we are having two charges over here, and this is the midpoint of charges, condition 1, and a charge is placed at the midpoint between the charges. So if I am going to calculate the force due to discharge, and force due to this charge. The forces are equal and opposite, and the effective force on this charge will be 0. But what happens if I am going to displace the charge Q1 towards right or towards left? Suppose we will see both the situations here. Suppose I have displaced the charge Q1 towards right. Q1 towards right. So the distance between this one and this one will decrease and the force will increase. Fine. Distance will decrease, the force will increase. If I am going to displace this charge towards left, again the same situation happens. In each situation, the force is acting in opposite direction. But the forces are not equal. One force is acting toward left, other is towards right, and they are not equal in magnitude because the distances are different. Their directions are opposite, but their magnitudes are not equal. So what will happen in this case? This is the condition of stable equilibrium. This will give you rise to a condition of stable equilibrium, and the charge will oscillate. What happens if I am going oscillate about this mean position, I say this one. If I am going to displace the charge in the upward direction, that is on the bisector of this one, see, this force will be acting this way because same nature of charge is there, and this force will be acting this way, and the resultant of these two is this. Because repulsive forces are acting over here, same nature of charges are there. So the direction of resultant force on charge Q1 is in this direction. So it will try to move away from the center. Either you consider that the position below this charge, the system of charge, the situation will remain same. Fine. Okay. Condition 2. Most of the times such problems are asked in JEE Mains in advance also. Suspended charges. Suppose two charges are suspended or two balls are suspended with charge with them in this way. Obviously point like charge you will consider here. And the distance between these two is r. The angle between them is theta. The charge is q. The charge is q over here. On the both bodies the charges are equal. And we need to calculate the angle. So such a system remains in equilibrium. So in the condition of equilibrium, what happens? You see the forces acting over here. First of all, the repulsive force away from the charge, that is q square by r square. The weight of the bob empty downwards, and the tension in the spring is T. Now you can see this angle is theta. So we can resolve the tension into its components. Obviously, this is T cos theta and this one is T sin theta. So since the system is in equilibrium, this force is balanced by this one this one is balanced by this one. So we can write here T cos theta is equal to mg and and T sin theta is q square by r square. So by solving these two or by dividing these two, we can be calculating the angle between them. What happens if I do situation A, situation B? If this system of charges is placed inside a liquid of some density without changing any of the condition over here, we are inserting the entire thing inside a liquid of some density. See, a liquid is there whose density is rho L, and the density of this solid is suppose rho S. Forces will remain same. This is T sin theta q square by r square T cos theta, but now the downward force, that is effective value of accretion due to gravity, because here not only the gravity is working but it is inside the liquid. So we have to consider the effective value of gravity, and in the condition of fluid mechanics, in the chapter of fluid mechanics, we have studied this G effective can be calculated mg 1 minus rho L by rho S. That is the density of liquid upon density of the solid. So this all we are considering the static charges. You must keep in mind. This all we are considering the static charges. I will take one situation in which a dynamic charges can be there. See, suppose on a ground level, we have projected a charge Q at some angle theta with the horizontal from the ground. Obviously, this charge will follow a parabolic path. That is, its motion will be a parabola. That is a projectile motion. If you consider the accretion due to gravity, it is acting downward. Suppose in this condition, we are having an external electric field acting over here. The electric field is acting in the downward direction. So in place of G, we have to consider the value of G effective, and here G effective will be G plus QE by M. Rest of all the condition will be just like the projectile motion. All the equations will be similar. In place of G, we have to take the G effective, and similar if the electric field is acting in the upward direction, the G effective will be G minus QE by M. Right? Okay. Thank you all.